Let us now draw the Lewis structures for molecules A to E as shown on the screen. Let us begin with molecule OF2. We first need to find the central atom, since we have more than 2 atoms. And rule number 1 says that the most metallic element is the central atom. Now, between oxygen and fluorine, oxygen is more metallic than fluorine, which means that oxygen will be the central atom, surrounded by the 2 fluorine atoms. Now, remember, metallic properties would increase from right to left, and it will increase from the top of the periodic table to the bottom. The next thing is to represent the valence electrons in each atom. Fluorine is from group 7A, so it will have a valence of 7. Oxygen is from group 6A, so it will have a valence of 6. Now, let us obey rule number 2. Rule number 2 says that we should complete the octet structures of the outer atoms before we look at the central atom. Now, each of the fluorine atoms in OF2 has 7 valence electrons. If fluorine shares 2 electrons with the central oxygen, and that goes for the second fluorine as well, and you look at the fluorine atom, you will see that the fluorine now has 8 electrons around it, so the octet is complete. The same thing goes for the other fluorine atom. It now has 8 electrons in its outermost energy level. Now we can look at the central atom. Before we do that, let us redraw this structure. This is going to give us oxygen with 2 lone pairs on it, and the fluorine atoms with each fluorine having 3 lone pairs of electrons. If you now look at the oxygen, you will see that the oxygen is connected to 2 bonds, which means 4 electrons, since each bond represents 2 electrons. And we also have 2 lone pairs, which is another 4 electrons. So around the oxygen, we also have 8 electrons. So this is the Lewis structure for OF2. That concludes question A. Let us take a look at question B. We want to draw the Lewis structure for BH3. Again, we need to know which is the central atom. In this case, it is clear-cut. Boron is the central atom. And the question is, why? Well, if you look at rule number 1, as we mentioned in the previous video, hydrogen cannot be the central atom. So, by default, in this structure, boron is the central atom. Now let us represent the valence for each atom. Boron is from group 3A. It's going to have 3 valence electrons. Hydrogen is from group 1A. It's going to have just one valence electron. Let us now obey rule number 2. We should complete the octet of outer atoms. In the case of hydrogen, we cannot have an octet. We can only have a duet, which means 2 electrons, because hydrogen can only accommodate a maximum of 2 electrons in its valence. So, how can hydrogen be stable? If it shares 2 electrons with boron, each hydrogen will become like helium, so they will be stable. Let us redraw this structure. Now let us take a look at how many electrons do we have around boron. We have only 3 bonds. There are no lone pairs, which means that boron only has 6 electrons in its outermost energy level. That is not an octet. But is that even allowed? In the case of boron, yes. Boron is an exception to the octet rule. Boron is an exception to the octet rule. Boron actually prefers only 6 electrons in its valence, and that is what we have here. The other element that is also an exception is beryllium. Beryllium only prefers 4 electrons. So beryllium is also an exception. Although we don't have that here, but please remember that. Let us now look at the final structure. This is the final structure. So that is the structure of BH3. And again, it comes with the understanding that boron is an exception to the octet rule. Let us now move on to question C. In question C, we want to draw the Lewis structure for HCN. Again, we need to first find the central atom. We have H, C, and N. Hydrogen cannot be the central atom. That leaves us with carbon and nitrogen. And if you look at the periodic table, since metallic properties increases from right to the left, carbon is more metallic than nitrogen, which means that carbon will be the central atom. Let us now represent the valence of each atom. Hydrogen is from group 1A. It will have only 1 valence electron. Carbon is from group 4A. It will have 4 valence electrons. Nitrogen is from group 5A. It will have 5 valence electrons. And then we need to complete the octets of the outer atoms based on rule number 2. For hydrogen, we only need to complete the duet structure. So hydrogen shares 2 electrons with carbon. Hydrogen becomes stable. However, for nitrogen, nitrogen has 5 valence electrons in its atom. If we share 2 electrons between nitrogen and carbon, that only takes nitrogen to 6 valence electrons. Then we need to share more between nitrogen and carbon, but we now have nitrogen with 7 valence electrons. If we share 2 more between carbon and nitrogen, that takes us to 8 valence electrons for nitrogen. Let us now redraw the structure. Carbon is sharing 6 electrons with nitrogen. That would be a triple bond. Nitrogen also has a lone pair that is not being shared. Then carbon is connected to hydrogen. Now let us look at the central atom, which is carbon. Carbon has 4 bonds connected to it. 4 bonds means 8 electrons. So this is the lowest structure for HCN. Let us now move on to question D. We want to draw the Lewis structure for the ammonium ion, NH4+. Hydrogen cannot be the central atom. By default, nitrogen is the central atom, surrounded by the 4 hydrogen atoms. Let us represent the valence for each of the atoms. Hydrogen will have a valence of 1. Nitrogen is from group 5A. It will have a valence of 5 electrons. Now let us complete the octet or duet of the outer atoms. If you share 2 electrons between hydrogen and nitrogen, the hydrogen will become stable, because then the hydrogen will have its duet of electrons. So each of the hydrogen is now stable. But there is one thing we are not taking into consideration yet, and that is the positive charge. A positive charge means that we should remove an electron. If it is +1, you remove an electron. If it is +2, you remove 2 electrons, and so on. So in this case, we have a +1, which means we should take 1 electron away, and I am going to take this electron away. So that electron has been taken away. And to indicate that an electron has been taken away, we will place a positive charge. Now if we redraw this structure, we will get that as the structure of ammonium ion. And that is question D. Let us now move on to question E. In question E, we want to draw the Lewis structure for the chlorate ion, Cl(O3) with a charge of -1. Between chlorine and oxygen, chlorine is the more metallic element. So chlorine will be the central atom, surrounded by the 3 oxygen atoms. We can place the 3 oxygen atoms anywhere we want. Let us now represent the valence of each atom. Oxygen is from group 6A. It will have 6 valence electrons in its outermost energy level. So each of the oxygen will have 6 valence electrons. On the other hand, chlorine is from group 7A. It will have 7 valence electrons in its outermost shell. Now the next is to complete the octet of the outer atoms. Each oxygen has 6 valence electrons. So if we share 2 electrons between oxygen and the central chlorine atom, the oxygen is not yet having an octet structure. So to make the oxygen happy, we would have to share more than 2 electrons. So we will need to have another 2 electrons being shared between the oxygen and the chlorine atom for each of them. But we are still leaving something out. We have a -1 charge. A negative charge means that we should add an electron to the structure. So let us add an electron. Now let us redraw the structure. Chlorine. Each oxygen is sharing 4 electrons with the chlorine, and each oxygen has 2 lone pairs of electrons that are not being shared. And chlorine itself has a lone pair. To indicate that we added an extra electron, we should place a negative charge. The last thing to check is the central atom. Does it have an octet? No, it does not. Let us count. If you look at the chlorine atom, it has 6 bonds connected to it. 6 bonds means 12 electrons. Then it has a lone pair, which means 14 electrons. Is that allowed for chlorine? Yes. That takes us to rule number 3. Elements from period 3, 4, 5, 6, 7 can accommodate more than an octet of electrons in their outermost energy level. Chlorine is from period number 3 in the periodic table, which means that it can accommodate more than 8 electrons based on quantum chemistry. So chlorine having only 14 electrons is okay. And those are the structures of the 5 examples we started out with.